Hey guys, welcome back. Welcome to week 2 of e-learning. We're going to be going over your CK12 reading and video stuff that you did last week for homework to preview today's lesson on reaction rate and collision theory. Okay, so let's start by just, take these notes. Again, we want to assume at some point you're going to be tested over this stuff and you'll need these notes. Um, so reaction rate, change in concentration of a substance over time. And it can be expressed a couple of different ways. The first thing we have to think about is what's happening over time to our reactants and products. In the beginning, we're going to have all reactants, so a high concentration of N2O5 in this case, and zero products, so no NO2 gas and no oxygen gas. So, of course, that means reactants are going to be going down over time, and it means products are going to be going up over time. So how can we express reaction rate? Well, we can measure this a couple of different ways. We can look at how quickly, let's say, for example, NO2 is produced, and we can say the rate of our reaction is the change in concentration of NO2. And remember, the brackets mean concentration of. So it's going to be change in concentration of NO2 over change in time. So maybe from 0 to 20 seconds for a reaction, the concentration of NO2 goes, well, what would it start at if it's a product at 0 seconds, right? It would start at 0, okay? So let's say it goes from 0 molar up to 0.015 molar. So if it starts at 0 and it goes up to 0.15, we do final 0.15 molar minus initial, which would be 0 molar, over time. And in the verbal example I just gave you, that was 20 seconds. So, and actually I think I said 0.015 molar. Sorry about that. So what would be the rate for that reaction? Okay, so I got 0.00075, and that's molar per second is how you would express that rate. Of course, you could also say 7.5 times 10 to the negative 4. All right, so that's an example of expressing reaction rate in terms of a product that's being formed. We could also express it in terms of the reactant. So the reactant, though, is disappearing. So what you would say there is, if I was to express the rate of the reaction in terms of the change in N2O5, because it's a reactant, it's going from a higher down to a lower concentration. So the rate of the reaction could also be expressed as the negative of, change in concentration of N2O5 over time. And again, that's just because, sorry, didn't realize I was concealing my work there. And that's just because the N2O5 is going away. So if I do final minus initial, like I did up here, I'm going to get a negative answer, right? So if it's starting at 0.5 molar and going down to 0.3 molar, final minus initial would be 0.3 minus 0.5. That's going to give me a negative answer. So if I take the negative of that, I get a positive answer. We will always get a positive rate. It doesn't really make sense to get a negative rate. Okay, so let's take a look at another example. Let's clip this out of a textbook, or pasted it from a textbook. So here it doesn't give us the reaction, but basically we've just got two substances. And in the jar in the beginning, and let's just assume this is a 1 liter jar, and that way all of our numbers of moles, if we just divide it by 1 liter, that gives us our molarity. So like, for example, 1 mole of substance A, if this is a 1 liter jar, well, that's going to be 1 molar, right? So we can very quickly go from moles to concentration if we assume it's a 1 liter jar. Okay. In the beginning, we have 1 mole of A and 0 moles of B. So if that is the case at time equals 0 seconds, um, then what do you think our reaction looks like? What are our reactants? What are our products? Okay, you should have said that the reaction is basically just this. A is our reactant, B is our product, because at time equals 0 you have no B, which makes sense because that reaction hasn't started yet, hasn't been given time to start. You have all of A. Okay, so if we want to find the rate of this reaction, let's say from um, 0 to 20 seconds. Um, let's go ahead and set that up. So let's say we're trying to find it in terms of change in concentration of A. So our rate in terms of A, and A is a reactant. So what are we going to have to remember to do? Reactants are always going to be going down, right? So we're going to have to put a negative sign out in front. So we're going to take the negative of our change in concentration of A over change in time, all right? And we're just going to go from 0 to 20 seconds, right? So right there, that's our change in time. So let's rewrite this uh, and say rate equals, and then and again, negative. And so our final concentration of A after 20 seconds would be 0.54 molar. Again, we're assuming 1 liter. So 0.54 molar minus our initial, which was 1 molar, and our change in time, 20 seconds. So go ahead and calculate that rate. Okay, so you should have gotten rate equals 0.023, and that would be molar per second as our unit. Okay. Now we could have just as easily done this same thing in terms of B. So going from 0 up to 0.46, but we wouldn't use the negative sign because it's a product. It's going up already. So it would just be 0.46 minus 0, so 0.46 over 20 seconds. It's the same rate, of course, because A is being used up at the same rate that B is being produced. And that's because the balanced equation has a 1-to-1 ratio. And we wrote the balanced equation, but that's one way that we would know that this balanced equation is a 1-to-1 ratio, because A is getting used up at the exact same rate as B is being formed. And we'll get back to that here in just a second. You'll see what I'm talking about. One thing I want you to notice, we're not going to do any calculation with it. We could very easily do the calculation of rate from 20 seconds to 40 seconds. But you might notice that even though the time interval is the same, it's a 20-second gap, that the concentration of A is only going down by what, 0.24, right? Whereas in the first 20 seconds it went down by 0.46. So the reaction seems to be slowing down, and that is perfectly normal. Just like in the reading, it talked about, I think it talked about cars racing, and you can have rate expressed as an average over the course of the entire race course, or you can talk about the instantaneous the instantaneous speed, meaning the speed as it crosses the finish line. Okay, so the reaction rate is not constant during this whole 40 seconds. Um, So when we talk about rate, it's always over a certain interval. It's not going to necessarily be a constant rate over the entire course of the reaction. Okay, the next thing that I want to talk about here is something that the online book didn't really address. It talked about the negative sign out in front of the reactants, but it didn't really talk about coefficients. And it's a simple concept, but what I want you to understand here, guys, is when there are coefficients other than one, that's going to affect how quickly that substance's concentration is changing. So what we set up above here with this previous example was that because A is disappearing at the same rate that B is being produced or appearing, then there must be a 1-to-1 ratio in the balanced equation. For every 1 mole of A that gets produced, for every 1 mole of A that gets used up, 1 mole of B gets produced in a given period of time. But what if we do have coefficients? Well, it's pretty simple. If I have a coefficient of 2 out in front of N2O5 and a coefficient of, let's say, 4 out in front of NO2, that means I'm going to expect the concentration to change faster for NO2 in a given period of time, or more dramatically in a given period of time, than it will for N2O5. Okay? So the way that this works is I can actually relate the rate of two substances to one another. Another way to say this is if we wanted to express the rate over, let's say, the first 20 seconds of a reaction in terms of N2O5, first of all, it's disappearing, right? So I'm going to say the negative of change in concentration of N2O5 over change in time, okay? Because it's going away. I could also express it in terms of, well, let's go to the O2. I think that'll be a simpler example. I could also express the reaction in terms of this oxygen, okay, which has a coefficient of 1. So I could say, all right, the rate of this reaction is equal to the positive change in concentration of oxygen over time. So it's positive because it's a product, it's going up. But these two rates would not be equal to each other, and that is because of the coefficient in front of the N2O5. The coefficient in front of the N2O5 means that it's going to get used up twice as fast as the O2 is produced. In other words, its change in concentration will be twice as dramatic because it takes 2 molecules of N2O5 to produce 1 molecule of O2. So hopefully that makes sense. So if I wanted to actually relate the rate of disappearance of N2O5 to the rate of appearance or production of O2, I would have to factor in that coefficient. And the way I would do that is actually pretty simple. I would simply say, in order to make them equal to each other, here's what I would say. I would say that the rate of disappearance of N2O5, so the negative change in concentration of N2O5 over time is equal to the change in concentration of O2 over time, but only if I add a 1/2 out in front of the N2O5. And again, that's because in order for me to say that these two are equal to each other, I have to cut this change, this value in half, because in fact, it's going to be changing twice as fast. And so by multiplying by 1/2, then that allows me to say that these two values are equal to each other. Okay, so that is just an expression of rate relating the rate, the rate of reaction, the change in concentration of two substances within the same reaction to each other. And again, I got this 2 this denominator for the 1/2 from that coefficient. So if I were to do the same thing, but this time let's say we were comparing the rate of production of NO2 to the rate of production of O2, what are some things that we would have to keep in mind? Would either of them have a negative sign out in front? So you should say no, they're both products, they're both going up in concentration, right? So if I wanted to say the change in concentration of NO2 over time is equal to the change in concentration of O2 over time, I'm going to have to multiply one of them by a fraction, right? And that fraction would go, what would it be and where would it go? Okay, hopefully you said that because there are 4 NO2s produced for every 1 oxygen, in order to make this equation true, or this statement true, we would actually have to multiply this first one by 1/2. Pardon me, 1/4. Because again, this NO2 is you're producing 4 times as much of it. So in order to make this statement true, you'd have to multiply the change in concentration of NO2 by 1/4. The other way to do it, of course, would be to multiply the second one by 4. But generally, just as convention, or by convention, it's done as fractions. Okay. The last thing we have to talk about is oh, I'm sorry. We have one more example problem. So it says write the equation that relates the rate of production of NH3 to the rate at which hydrogen is used up. So go ahead and try that on your own. Okay, so if you said your NH3 would be multiplied by 1/2, so 1/2 the change in concentration of NH3 over time is equal to 1/3 the change in concentration of H2 over time, and I forgot one thing, and of course that is my negative, right? The H2 is going to go down, and so it's going to have a negative change. Okay, the last thing we want to talk about is collision theory. This concept is pretty simple, pretty straightforward. All right, so collision theory, there are your notes, and that picture is borrowed actually from the reading, the CK12 reading. But in order to react, particles must collide with enough kinetic energy to break the existing bonds. Very simple. If these particles, these two molecules, have the potential of making these products down here, but they don't collide with enough energy, they simply bounce apart. If they do, we get products. Very simple. Right? So that's the first stipulation of collision theory. The second stipulation is they have to collide with correct orientation. So hopefully you watched the video in addition to doing the reading. Um, the teacher video that had some examples, but basically it was like, if you have particles that are oriented in a couple of different ways, when they collide with one another, when they do this, they come together. If they're in this orientation, maybe they don't react. If they're in, this orientation, again, maybe they don't react when they collide, no matter how much kinetic energy they have. But let's say that for this particular reaction, when they come together so that they're sort of all lined up, you get a reaction, okay? And maybe your products are like, one of each. So you have like a new set of bonds forming. All right, so that's what we mean by orientation. They have to collide with the correct orientation. And that's just completely random chance, right? And we'll talk about how to affect reaction rate here a couple sections down the road. But essentially, what collision theory is all about is successful or effective collisions versus unsuccessful or ineffective collisions. So what I've drawn down here would be an example, assuming the kinetic energy was high enough, this would be an effective collision. So you have to have enough kinetic energy, so the particles have to be moving fast enough, and we have to have um, the uh, the correct orientation. Those both have to be in place. So I'm going to insert a couple of questions here. Just a lot of them are actually from the practice that you already did, and just to kind of test a few terms and concepts about collision theory. Okay, guys, I know that that was a long video, long ed puzzle, but you're only getting two of these a week, so hopefully you can handle that. We're gonna go instead of once a week, I'm gonna do two a week. We're gonna do a couple sections from the text, or from the the CK12 online text, and then my notes along with ed puzzle questions. Make sure you're doing the practices within those CK12 assignments, um, and those will be graded, or at least you'll get points for having done them. You just basically have to get 10 correct. Um, and then yeah, we'll be doing this every Tuesday and Thursday instead of just on Thursdays. So this assignment will be due on Tuesday morning, and then Tuesday morning you'll have a new one for Thursday morning, or that will be due Thursday morning. So good luck. Please attend our Zoom sessions if you have any questions, and email me also if you have any questions. Thanks, guys.